Good morning, everyone. Sorry I'm a little bit late. I was writing an email and I lost track of time. Wow, that's incredibly out of focus this morning. So this is CHL 311P5. There we go. How many do I got? Okay, I got 15. I'm going to start. All right, hello class. So last time we learned a couple of equations. So we learned about the definition of electric potential, which is U of x divided by Q equals V of x. So U of x is the electrical potential energy. V of x is the electric potential. And Q is the size of the charge. Okay? So if you take the derivative of this, you are able to discover the relationship that the electric field is negative the derivative of the potential with respect to position. And by integrating this equation, you are able to show that VB minus VA is negative the integral from a to b of E dx. Okay? So these equations tell us a lot about units. Okay? So in particular, it says that the units of electric potential are units of potential energy, which are joules, divided by units of charge, which are coulombs. Okay, so electric potential is measured in joules per coulomb, but this has a special name. It is defined as the volt, V. Okay. This equation also gives us a second unit for electric field. So originally, we have used the unit for electric field newtons per coulomb, okay? But this equation gives us another equivalent unit, which is, because we can see that electric field is electric potential divided by distance. So electric potential is measured in volts. Distance is measured in meters. So another common unit of electric field besides newtons per coulomb is volts per meter. Okay? 1 newton per coulomb is exactly the same as 1 volt per meter. So it's just a name difference. Okay? But I just wanted to make sure you're aware that volts per meter is a common alternative. Actually, it's probably more common than newtons per coulomb, I would say. All right. And then we talked about what is the electric potential due to a single charge, which is KQ over R. Okay, so that's for a single charge. All right. And then if we want to know, like, let's suppose we have a number of charges. So we have Q1, Q2, maybe Q3, something like that. And what if I wanted to know the electric potential right here at the point P? Well, what I would do is I would look at what is the distance of Q1 from point P, and I would call that R1. And then I would look at what is the distance of Q2 from point P, I would call that R2. Q3 from point 3, I would call that R3. Okay. And then the potential at point P, due to all of these individual single charges, would be the sum over all the charges of K QI over RI. Okay, so that's how you that is how you compute the electric potential due to a discrete set of charges. All right. Today's lesson is about computing the potential due to a continuum distribution of charge. Okay, that's the topic of today's lesson. So what is a continuum distribution of charge? Well, a continuum distribution of charge is, of course, a blob of charge, something like this. And let's just focus in on a little tiny portion of that, okay? So this little tiny portion of the charge distribution has a charge dq, all right? And let's say we're trying to calculate the electric potential right there, all right? So what we would do is we would look at what is the distance of dq from point P, and I would look at that. I would measure that distance out and call that R. All right? So the potential created at point P by dq, I'm going to call that dV. All right? So remember, d means an infinitesimal amount. So an infinitesimal amount of charge is going to create an infinitesimal amount of potential at the point P. And that is equal to just the same formula, K dq over R. All right? The only difference is it's just a really small amount of charge. Now, what do we do if we want to know what is the total electric potential due to all of the charge distribution at point P? Well, we have to sum up all of the contributions. So from this little bit of charge, 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 add them all up. And the calculus term for that is integration. Okay? So the potential at point P is going to be the integral of K dq over r. All right. And so this is the main formula that we are going to play with today. All right. And so what we want to remember is that we are going to write dq in terms of something else. Okay, so for example, if we have a line of charge, if you have a line of charge, you might write you might write something like lambda dx equals dq, something like that. If you have a plane of charge, you might write it as sigma dA equals dq. If it's a volume distribution of charge, you might write rho dV is equal to dq, etc. Okay, so you're always going to write that in terms of something else. And then you are going to basically find an expression for R in terms of integration variables. So R is a function of the integration variable. So for example, it might be a function of x, it might be a function of angle, it might be a function of y, and so on. Okay, so yeah, we're just going to play with this. We're going to do a couple examples of how this works. And the really nice thing about working with electric potential is that electric potential is a scalar, which means we don't have to worry about the direction of the electric potential. We had to worry about that when we were talking about electric fields, but we don't have to worry about it with electric potential, so that makes it real nice. Okay, so man, it's cold in my house. I need to go close the door. Okay. So let's do an example. So let's suppose we have a uniform line of charge. Of length L and charge Q. And let's suppose that it starts at x equals A. All right. So naturally, it would extend to x equals A plus L. All right, because it is a it has length L. So let me draw this out. We want to know what is the potential at the origin. So what is V of 0? Okay, so if this is the origin, if this is x equals 0, then the line of charge starts at x equals A, and it extends to x equals A plus L. All right. And so what we want to do is we want to consider a little itty-bitty piece of charge, dq, at coordinate x. This distance right here because we're measuring the electric potential at the origin, the distance between the origin and x is just x. So R equals x. All right. And then furthermore, we're going to have lambda is Q over L, which is a constant because it's a uniform line of charge. So that means that dq is Q over L dx. All right, I'm using this equation right here. All right, so then I can just plug in, so the potential at the origin is going to be the integral of k times Q over L dx. So this is our dq, and then divided by r, which is equal to x. Okay, so this is the exact same formula as I have right here. My integral is going to go from a to a plus L. X being my integration variable. Oh, el gatito. Hola, el gatito. Hola, el gatito. Oh, hola, el gatito. So I can factor this part out because that does not depend on the integration variable x. So I have kq over L times the integral from a to a plus L of dx over x. That's, of course, going to give me natural log. And so my final answer is going to be kq over L times the natural log of a plus L over a. Bug just ripped one. So that is my final answer. Okay. Moving right along to our next example. All right. Let's suppose we have a ring of charge of radius r. Oh, and it's going to be a uniform ring of charge. Okay. Okay. It's a uniform ring of charge of radius r and total charge q. All right. And so let me draw this from like a 3D perspective. So from a 3D perspective, you've got your ring of charge. It has a radius big R. Okay. And here's the axis of the ring of charge. Okay, this is a right angle. And we want to know what is the electric potential right here at point P, where point P is a distance y above the ring. Okay. So, and then if I think about this from a side view, it's going to look like this. Here's the ring, and then here's the point P. This distance is y. So if we think about it, the distance from this little bit of charge, dq, okay, to the point P is square root of y squared plus r squared. Okay? Right? So here's our little bit of charge. The radius is r. this distance by the Pythagorean theorem is square root of y squared plus r squared. All right. That's the point P. Now, here's the interesting thing. Just like before, when we did the ring of charge with the electric field, any little piece of charge on this ring is the same distance away from point P, because it's like a cone. If I pick this point over here, it's the same distance away. Okay, this point is the same distance away. This point is the same distance away. It's making a cone. Okay, so all the points of charge have the same distance away. So if I want to know what is the potential at the point P, is going to be the integral of k dq over little r, which is square root of y squared plus big R squared. All right. And so excuse me. So now what we want to notice is that all the little itty-bitty pieces of charge are the same distance away. So we can actually factor out this, okay? Because it doesn't matter what y is, it doesn't matter what r is, they're all the same distance away. All right, so we just get k over square root of y squared plus r squared times the integral of dq. Now the integral of dq is just the sum of all the charge, right? Because integral stands for sum, and we're talking about the sum of all the charge on the ring, so that's just going to be q. So our potential at point P is going to be kq over square root of y squared plus r squared. Isn't that nice? So that's super easy. So I want to do a little extension to this problem, which I think is interesting. All right. So let's imagine this from a side view. Okay. So we have this ring of charge Q, and we're looking at it from the side. All right. And what if I put a charge of size negative little q right here? All right. A distance y above the axis. Now what you can imagine is, because this is a ring with charge positive q, this negative charge is going to get attracted towards the center of the ring. It's going to get pulled down. But because of its inertia, it's not going to stop at the center. It's going to actually swing through, and it'll end up on the other side. And then once it's on the other side, the ring is going to pull it back up, and it's going to execute simple harmonic motion. Okay? So it's a side view of a charge negative little q at location y on the axis of the ring. Okay? And so it is going to undergo simple harmonic motion. And so what I want to know is, what is the period of that simple harmonic motion? All right. So I love these types of calculations. I don't know why, but I do. So what we want to do is we want to use this formula, and we're going to notice that the potential energy of this charge as a function of y is going to be the size of the charge, which is negative q, times the potential that it experiences, right? This is the very definition of electric potential. If I take the electric potential and I multiply by the size of the charge, I get its electrical potential energy. Okay? So I'm going to use this formula right here to get its potential as a function of y. And so I get negative k little q big Q over square root of y squared plus r squared. That is the potential as a function of y. All right. Now, if you recall, we talked about small oscillations. And I said that no matter the shape of the potential, okay, if you have an equilibrium point, a particle will undergo simple harmonic motion about that, okay? So in the center of the ring is the equilibrium point, right? Because if you put a negative charge right at the center of the ring, it's being pulled equally in all different directions, so it just doesn't move, okay? So that formula I gave you was period is 2 pi square root of m over u prime prime of the equilibrium point. The equilibrium point is going to be y equals 0. Okay? Because that's, if y equals 0, then it's in the center of the ring and it's just not going to move. So we have to do the second derivative of this function with respect to y. So let me do the first derivative. So u prime is going to be minus k little q big Q times negative 1/2 times 1 over y squared plus r squared to the 3/2 times the derivative of y squared, which is 2y. Okay, so my u prime is k little q big Q times y over y squared plus r squared to the 3/2 power. Okay, so now I have to do the derivative again. This one's not going to be fun. K little q big Q. So now I have to do the quotient rule. So low d high, which is just the derivative of y is just going to be 1, minus high d low, so that's going to be 3/2 times y squared plus r squared to the 1/2 times 2y over low squared. Okay, so that's a little quotient rule for you. Oops, squared. All right, so now here's the nice thing, is we are evaluating this at y equals 0. So see how it's this second term here, the term where all the nastiness was? That's y times something. So when I evaluate it at y equals 0, this term just goes away. All right. This term, when I plug in y equals 0, I get r squared to the 3/2, which is just going to be r to the 3rd power. And when I do this one with y equals 0, I get r to the 6th. So when I evaluated at y equals 0, I get k, little q, big Q, r to the 3rd divided by r to the 6th. All right, which is just k, little q, big Q over r to the 3rd, which I then plug into this formula, and I would get, so that's u prime prime of the equilibrium. So I would get 2 pi square root of, and it's 1 over u prime prime, so I'm going to flip this fraction, m r cubed over k, little q, big Q. I think that kind of calculation is just fun. I don't know. I like calculating periods of small oscillation. I don't know. It's I don't know why. It's just always been one of my favorite things to calculate. I don't know. I just like it. So today's quiz doesn't have this type of a problem on it, but the next quiz, Monday's quiz, will have that type of problem in it. So let's do one last example. What if I have a uniform disk of charge Q and radius big R? So exact same problem. So I want to know what is the potential as a function of y. Okay. So I have, so the difference is, here's the axis of the disk. Here's the center. Okay. Boom, like that. There's my point P. It's a distance y. All right. And so we want to know what is the potential right there. So what I'm going to do is, first of all, because this is a disk of charge, I'm going to have sigma dA equals dq. All right. And so because it's a disk, my area is pi r squared. And so that's the area. And so dA is going to be 2 pi r dr by taking the derivative like we have before. So I get sigma times 2 pi r dr is dq. Okay. And then what I want to do is I want to imagine a little tiny ring of charge right here. And that ring of charge has radius little r. And we know that the distance of this ring from the point P is going to be square root of y squared plus little r squared. Okay? So that is going to be my my distance. So when I do the integral of k dq over r, my r value is square root of y squared plus little r squared. All right. And then my dq is sigma times 2 pi r dr. All right. And my limit of integration is going to go from 0 to the entire radius of the disk, which is big R. So we can see that little r is my integration variable. So anything that doesn't depend on little r I can factor out. So I have 2 pi k sigma times the integral from 0 to big R of little r dr over square root of y squared plus little r squared. Like that. And then you just do the calculation. Okay, this is a really easy U substitution integral. I'm not even going to do it. I think I'm going to stop my lesson there. If you didn't understand the uniform disk, that's okay. My quiz for today only has lines of charge and rings of charge and stuff like that, so I wouldn't worry about it too much if you don't understand how to do the whole dA thing. It's a little bit more advanced. So that's my lesson for today, and I will see you in the Zoom room for some announcements.